Welcome to massive open online course on chemical process intensification. So, we are discussing something regarding process intensification by interfacial area under the module 8, and in this lecture we will try to discuss more about that interfacial area based process intensification, and it will be regarding the ejector induced downflow system for process intensification. Now, in this lecture we will discuss that how to configure the downflow system for the process intensification, and for that how ejector is being used actually for creating that cavities or bubbles or droplets, and also how it can actually suck the gas to disperse it through the pool of the liquid, and also how create that surface area to intensify the mass transfer or any other chemical engineering processes. And in this case, very interesting point that ejector is the one important characteristic factor by which you can use the gas to disperse in the liquid, so that it will be dispersed in such a way that higher mixing will be parallelly happened in the system, and so that due to that interfacial mixing, that intensification of the process can be obtained. Now, we will systematically discuss regarding that. First of all, that whenever you are using this ejector system, that can be used in upflow, downflow, even that horizontal flow system to perform any chemical engineering processes. So, first of all, here we will try to discuss the process intensification by the downflow system. Now, what is that downflow system? Now, you will see that in this slide we have given here one picture of downflow system, where you will see that this is the unit that carrying out reactions and mass transfer operations, in which you can get the gas which will be made of one or several reactive components that come into a contact of reactants with a liquid. In this case, you will see that it can be characterized by the fact that the gas is dispersed in the continuous liquid phase in the form of bubble against its buoyancy effect by downward liquid momentum. What does it mean actually? What I wanted to say here, that you will see if we make a unit like this here, this part is ejector system, and this part is that contactor, and this part is separator system. So, if we make a downflow system in such a way that the liquid will be flowing downward system through this unit, and during the downward movement, that liquid will be made a jet in such a way that it will be passing through a that suction chamber. So, whenever liquid jet will be coming out from this storage tank by a pump through the rotameter at a certain velocity, whenever it will be coming through this that nozzle, and this nozzle will give you that jet velocity, and whenever this jet velocity will come through this suction chamber, where one inlet will be there in the suction chamber, through which gas or atmospheric air may come whenever liquid jet will be passing through this suction chamber, and it will come through this ejector system, where the pressure recovery will be done when pressure will be produced during this jet. So, in this case the jet will be automatically suck the gas which will be carrying along with that liquid jet through this ejector, that is here one throat section, here diverging section, and through this ejector unit will be coming out, and it will be, if it is plunging in a pool of liquid in the contactor, you will see there will be a formation of bubbles, that means gas bubbles, which is actually suctioned by that liquid jet, and then that gas bubbles will be carrying downward by the downward liquid movement. And this movement of gas bubbles, whenever it will be coming downward, it will have you know that more residence time. Even at this location there will be intense mixing of you know that gas liquid there. So, based on this concept there is a process intensification by having more residence time, where the you know that some physical operations are required more, you know that contact times or residence time of the gas bubbles there. So, in this way you can use this downflow system. So, whenever this liquid gas will be coming out along with that, you know, carrying that you know gas bubbles by this liquid movement downwardly, and then it will be, you know, separating in a separator, and from this separator gas will be coming out through these sections. So, this way the gas is coming in these sections, and gas is coming out at this section, where liquid will be, you know, coming into the unit as a liquid jet, and which will be, you know, that plunging into the pool of the liquid in the contactor as a dispersed phase of bubbles will be formed, and which will be coming downward through this downward liquid movement. So, this is the characteristics of the downflow system. So, we can define this downflow system in such way that the one unit which will be carrying out reactions and mass transfer operations, in which a gas that will be made up of one or several reactive components that will be comes into, you know, contact or react with the liquid, and they are characterized by the fact that the gas will be dispersed in the continuous liquid phase in the form of dispersed phase of bubbles against its buoyancy effect, so that it can get the more residence time there. And in this case you can produce more finer bubbles also. Instead of gas, if you use some, you know, that secondary fluid as you know the some other immiscible liquid like kerosene, paraffin or other liquids which will be miscible with the water, then you can produce that droplet of that immiscible liquid, and that may also go downward by this liquid movement, and that droplet may be useful for the, you know, extraction of the unwanted material in the liquid or water. So, that also can be applied in this downflow system. So, this is the concept of this downflow system. Now, how to disperse that gas downwardly in the liquid, that we have already discussed, that there will be some entrainment of the, you know, gas whenever liquid jet will be plunging into the pool of the liquid in the column. So, by entrainment entraining that gas by the downward liquid jet, this you know downwardly liquid will disperse the, you know, gas as a dispersed phase of bubbles. And in this case, that sucking the gas by the liquid jet is happened through the ejector system, and then it's plunging into the pool of the liquid. After that, you will see whenever liquid jet will be, you know, that plunging into the pool of the liquid, it will break the bubbles into finer bubbles after entraining into the pool of the liquid, due to the high, you know, that turbulence and also high mixing there. So, breaking the surface of the pool of the liquid and entrapping the gas into the liquid as a bubble happened in this, you know, that contactor system after ejector system. And then what happened, that whenever bubbles will be forming or droplet will be forming in that intense mixing zone, by entraining of that gas or entrapping of the gas by, you know, entrainment mechanism, then it will be dragging downward by the downward liquid movement there. So, in this case the ejector technology is the most important you know driving force for getting the process intensification in this downward system, or the technology based on that ejector system. So, what is that ejector? We can define that ejector is an you know device that uses the expansion of a high pressure that is created by the fluid to entrain, and also compress a low pressure, that is suction there fluid by means of momentum transfer between the two streams of the fluid. So, here in this figure it is shown that you will see there will be a two fluid, one fluid will be motive fluid, and that fluid will be, you know, act as a fluid jet, and it will be passing through a nozzle here shown here figure, and whenever it will be coming out through the nozzle, a jet, liquid jet will be produced, and that liquid jet will be coming downward through a section that is called suction chamber. Now, this suction chamber, whenever this liquid jet will pass through this suction chamber, there will be a dragging of the liquid or sucking of the fluid, sucking of the gas, that is maybe different types of gas, or maybe that directly atmospheric air, that will be sucked by this liquid jet, and it will be coming through this mixing section here at this location, and after that it will go through the diverging section. You will see there, in this case there will be high pressure creation, and this diverging section there will be a low pressure creation. So, in this case here, whenever the liquid will be sucking gas, it will come out through the liquid, and it will be entraining in the contactor later on there. In this case, in this contactor there will be a pool of liquid, where this liquid jet will be plunging and this sucking gas will be entrapped in the liquid. So, this can be used that several chemical engineering operation there. So, and this motive fluid is expanded through a usually converging diverging, that is through sometimes converging only also, nozzle to high velocity and low pressure. And high that velocity and the low pressure is used to entrain that suction fluid through the suction nozzle, and the motive and the suction fluids are then mixed in the mixing section. And also you will see that high speed mixed flow is then decelerated in the diffuser, and static pressure is recovered, that is resulting in a pressure increase provided to the suction stream across the ejector. And in this case you will see exponentially increasing the interest in the ejector technology because of this mechanism for the formation of the fine bubbles or gas that is entrained and dragging downward through the liquid medium by that downward liquid momentum, and also getting the advantage of more surface area as well as more residence time. So, that is why exponentially increasing this interest in the ejector technology since 1995, that contains the keyword ejector. Now, there are several different types of ejector system. Mainly two phase ejector for heat recovery is used in that compression repression system there, vapor compression repression refrigeration system there. So, in that case the two phase ejector is generally used to refer to ejectors being used for work recovery in the refrigeration system. In that case, significant research has been done on the use of single phase or vapor jet ejector system, which are commonly employed in heat recovery refrigeration cycle. And that what is that standard ejector cycle? In this case, the most common vapor compression cycle that used this ejector for the work recovery is shown in the figure for the transcritical operation there, and this critical that cycle is referred to as that standard ejector cycle there. So, here in the figure it is shown that here see this is the ejector system, and this through this ejector system that gas is coming through this ejector, and that through ejector and as a jet, and then it will be that separated in the separator, and then that by compressor this that compressor the gas will be supplied here through this, and here again that from this separator liquid will be passing through that evaporator section for controlling the temperature, and it pass through this that ejector system, and then this way that this continuous cycles will be applied there, where this pressure how it will be changing at different locations that is given in this with respect to specific enthalpy. At this location 1, here you will see this pressure will be there, and then 1, 2, 3, here 4, 5, and then that 6, 7, 8, 9, and then 10. According to this cycle that ejector compressor system, even evaporator system, then how this pressure is changing with respect to different unit whenever ejector system is being used for this that vapor compression refrigerating system there. So, this is one important application of the ejector system there. And in this case, the standard ejector cycle, the expansion of the high pressure fluid from the condenser or gas cooler is used to entrain and lift the pressure of the fluid at the evaporator outlet. And then this result will give you the higher compression suction pressure and reduced compressor power that compared to a direct expansion or conventional expansion valve cycle there. Now, another important application of the ejector system in the chemical engineering or even biochemical industry, it is called that ejector loop reactor ELR. In this case, it is a superior alternative to the conventional start tank reactors. You will see that the start tank reactors you are using that mechanical device to start that fluid in the reactor, whereas in the ejector system that advantage is that you can have the advantage of producing high shear inside the reactor and mixing inside the reactor, as well as the formation of cavity and that formation of more finer bubbles and more interfacial area there. So, that is why it will be that advantageous relative to the conventional start tank reactors. And in this case, this type of reactors brings large amount of gas reactant into the contact to the liquid phase. And in this case, you can produce the more finer bubbles, that is called micro bubbles of around 20 to 60 micrometer, which give you the high efficiency, high energy efficiency production of that interfacial area. And in this case, high throughput capacity also can be done for the chemical engineering operation or even biochemical industry. And also in this case, this application of this ejector loop reactors will be advantageous because of getting the volumetric mass transfer coefficient relatively higher. In this case, KLa up to 2 orders of the magnitude higher of 5 to 50 second inverse compared to the commonly used gas liquid contactors are there. And it is reported by that Ughelli et al. In 2018 in engineering journal and life science sections there. So, I think it is very interesting that ejector loop reactors, how ejectors is being used to produce that finer bubbles, more interfacial area, more mass transfer, more that volumetric mass transfer coefficient, so that you can get higher order of that process efficiency in this ejector loop reactors. And this is achieved by mechanical that co-location of the gas phase in flow to the point where a maximum shear of the motive fluid occurs there. And it is highly recommended for the following types of reactors as shown in the slides, like amination, alkylation, even ethoxylation and hydrogenation, even carbonization, nitration, oxidation, etc. Several chemical processes are being carried out in this ejector loop reactor system. In the case of bioprocess, in this case the bioreactor can be treated as one of the most advanced ejector loop reactor. In that case, insufficient oxygen transport and shear stress induced growth inhibition are limiting parameters during the microbial fermentation process in the bioreactor. And the ejector loop reactor is beneficial on biomass, and you can consider that it will be a recombinant protein production due to its better mass transfer characteristics. And also you can get the maximum mass transfer coefficient values of 207 and 205 our inverse at power inputs of 6.9 to 9.7 watt per liter, where it is reported in ELR and STR respectively by Ughelli et al. 2018. So, we can say that this ELR system for biotechnological application, you will see for the fermentation process you can get the maximum mass transfer coefficient relative to that that start tank reactor. And since we are talking about that ejectors, of course, there are several configurations of that ejector systems. In this case, that we are having generally upflow, downflow and horizontal systems. In the figure, it is shown that this is your that upflow systems. From the bottom of the column, ejector is attached, so that the gas will be sucking by that liquid jet from this that inlet, and whenever liquid jet will be coming up and then gas will be automatically sucked by this liquid jet, and then it will be dispersed in the column, and then it will be separated in a separator. And also you can say that the liquid will be coming out from that separator can be used again as a that liquid inlet through this nozzle as a liquid jet. So, that continuous operation of this upflow can be possible. Here also this horizontal system also can be done here. This is the configuration of this horizontal here. In this case also these ejector systems are being used to get that liquid jet and sucking that gas from this portion here, and then it will go through that diffuser sections and then producing that finer bubbles, and then it will be coming in a separator which will be separating that gas and liquid in these two outlet streams. And then liquid again you can use as a that continuous manner through this nozzle again to get that continuous operations of that processes. So, in this case very interesting that upflow horizontal, but in this upflow and horizontal system you will not get that maximum that residence time distribution, whereas in the downflow systems you can get that maximum residence time distribution, because in this case that whenever this liquid jet will be sucking gas and producing that finer bubbles, it will be going downward through this downward liquid movement. And during that movement of that gas bubbles, whenever you will see that just balancing that buoyancy effects of that bubbles, it will go downward. So, at a certain operation you will see some bubbles, those who are not going upward against that its momentum, liquid momentum, and or some bubbles are not going downward because of this higher buoyancy effect. So, there will be a balance of that buoyancy effects and downward liquid movement, by which you can get the residence time of the bubbles in that particular location for long time. Even if you are producing more finer bubbles, it may go downward through this downward liquid momentum, but if your bubbles are bubble size in such way that the balance of this buoyancy force and its downward momentum are there. So, those bubbles will be that residing on that column for a longer time. So, in this way you can get more residence time of the gas inside the column, where that slow reactions sometimes it is recommended for getting more residence time or longer time to get the more mass transfer there. So, this is so in this way downward system here a liquid jet will be sucking liquid, and in the separator the liquid will be coming out from this portion, and gas will be separated and it will be coming upward in this location. So, this is the downward movement or downward configuration of the ejector system. And then also you will see that the two phase dispersion issuing out of the ejector is either sent to the separator or a reactor vessel or a holding tank, which provides additional contact between the phases. So, that is why it is more important or more advantageous processes based on this that ejector system. And in this case the motive fluid jet that will perform into two functions, like that it develops suction for entrainment of the secondary fluid, and also provides energy for the dispersion of one phase into the other. And in this case the ejector produces higher mass transfer rates by generating smaller bubbles or droplets if you are applying liquid liquid system, which can then be injected into a reaction vessel, thereby further improving the contact between the phases. So, in this way that you can intensify the chemical process by ejector system. And in the chemical industries, you will see that ejectors are used to entrain and pump corrosive liquids, slurries, fumes and dust laden gases, which is otherwise very difficult to handle. And jet ejectors can also be used for mass transfer operations like gas absorption or stripping and also others. Now, here you will see, as per Balamurgan et al. Reported in 2006 that many gas liquid operations that employ sheep trays can possibly be retrofitted using several ejector systems, as shown in figure here A, and you will see you can use also several ejector systems in B, as shown here, to generate that higher mass transfer coefficients and thereby get higher throughput from existing columns there. So, this is the recommendation to get the more that process intensification by these ejector systems in the replacement or retrofitting by these gas liquid operations in the distillation column or other gas liquid contact system. And in the chemical exchange process producing heavy water, in that case, a synthesis gas mixture of nitrogen and hydrogen is actually generally come in contact with the liquid ammonia at high pressure and low temperature. And in that case, the deuterium absorption from the gas mixture into the liquid ammonia that takes place in the presence of KNH2 as a catalyst there to get better mass transfer, then this sheep tray is replaced by the ejector system. So, this is one of the important application part where you can get the process intensification by these ejector systems by replacing that sheep tray gas distributor by this ejector system. And in that case, of course, you have to use the catalyst particles where it will not be treated by this high liquid jet by ejector system. So, that should be taken care for these processes. And now, what are the advantages of this ejector induced co-current downflow system over the other conventional devices? In this case, you will see for this downflow system, ejector system need no compressor for the gas entrainment, and higher gas resistance time you can obtain, higher contact efficiency between the phases you can get, coalescence of bubbles will be very negligible, even bubbles are finer and more uniform in size, you can say, higher mixing efficiency, even you can get the large interfacial area available for the heat, mass and momentum transfer there. So, these are the some important advantages of this ejector induced co-current downflow system over other conventional devices. Now, this see the ejector system to entrain gas in a column here, as shown in figure. It is shown that how this liquid jet is producing finer bubbles there. So, this is the storage tank. From this storage tank, this liquid will be allowed to pass through this rotameter, and this rotameter will give you the measurement of the that liquid flow rate, and also after that this liquid will be coming through this nozzle, and this nozzle will produce that liquid jet and will come through this suction chamber. In this suction chamber, air will be automatically sucked by that liquid jet, and then it will pass through this ejector system, and where in this ejector system that whenever liquid jet will be coming in contact with the pool of the liquid in this section, then it will produce that finer bubbles, and those bubbles at this location there will be intermixing, and then due to the downward movement it will be go downward, it will go downward, and it will come downward up to that separator, and in this case the contactor will be extended in the separator up to certain length, because here to get that liquid pool here above this contactor, so that the pressure will be generated in inside the separator, and due to that pressure generation this liquid will be go up into the column. by that high pressure there, and through this outlet, that gas whatever it will be separated in this separator from this liquid, it will be coming out to there. So, this is the process by which you can produce that finer bubbles and get the gas liquid contact by intense mixing and the more interfacial area by this ejector system. Now, there will be certain operational flow regime map, so that you can get this stable operation for this. So, for this down flow system, to get this stable operation, you have to maintain this that certain superficial liquid velocity and superficial gas velocity you can get from this flow regime map at which superficial liquid velocity and superficial gas velocity you can obtain that that stable operation of the down flow system to get more finer bubbles and more residence time for this air water system. And what are the mechanism of that gas entrainment by that liquid jet whenever that it will be plunging into the pool of the liquid. So, whenever liquid jet is coming into the pool of the liquid, you will see there will be thrust of the liquid surface, and because of that downward movement of that thrust, force applied by this liquid jet on the pool of the liquid, and then you will see that force will break that surface of the liquid, and after that breaking of this pool, this liquid jet thus entraining that gas in this location, and finally it will be entrapped into the pool of the liquid, and in this way you will see that there will be a entrainment of the gas is happened in the liquid. And then this mechanism, of course, whenever you are applying that liquid jet, you have to maintain a certain liquid velocity, so that you can get this minimum condition for getting this entrainment of the gas. What is that minimum condition? So, minimum entrainment jet velocity, that depends on the nozzle diameter and physical properties of the fluid. And according to Vende, Sende and Smith, you can say that this the jet velocity should be less than 5 meter per second. If it is less than 5 meter per second, then entrainment will not happen. So, jet velocity should be greater than 5 meter per second, and also for this if you are applying this that jet velocity for that surfactant solution, in that case this Vj should be is greater than that 10 sigma L by rho z dN. So, for the system where surface tension if you know and the gas density knows, and then you can calculate what should be the minimum jet velocity for the entrainment of the gas. And based on that entrainment ratio, that different authors they have done several investigation for that that gas liquid contact based on the energy how entrainment is happened based on that energy supplied there. So, that several investigator like this Vende, Sende and Smith, they got that entrainment gas entrainment ratio, that is QR, that is Qg by QL will be 0.19 to 1.2 if is jet Froude number is that 25 to 900. That in our system the present torque in this ejector system downflow system, we can get this QR ratio is 0.2 to 0.48 based on this Froude number of 14 to 1814, they are within this range. So, relatively better downflow system giving the better operational mode to get the process intensification for the chemical engineering process to more gas entrant into the liquid and get more that gas liquid contact and more interfacial area. There are several that correlations are proposed by different investigators based on that upward, downward, even horizontal movement system of this ejector system. And in this case some that whenever flow is upward, then how this mass flow rate of this gas entrained in the system, that can be calculated from these correlations. Whereas, for horizontal system, how gas is entrained and what will be the amount of gas is entrained in the horizontal movement, you can calculate from this correlation. And also for the downward system, that you can calculate that that gas entrainment amount by this correlation. So, remember this, whenever you are applying this downflow system, what are the different parameters that affect that entrainment characteristics there. One is geometric configurations like ejector, diffuser section, throat section, even you can say that nozzle, that is nozzle diameter is one of the important, because smaller nozzle will give you the higher jet velocity, that means more kinetic energy production, and based on which you can get the more mixing and more production of more entrainment of the gas and more finer bubbles production. And you can also say that there will be a that operating parameters like physical properties of the system there. If you use the higher viscous fluid, in that case you may get the lower entrainment of the gas, even lower entrainment of the fluid also. Suppose if you are willing to get the entrainment of immiscible liquid like kerosene in a that high viscous CMC solution, carboxymethyl cellulose. So, in that case you will see that kerosene entrainment will be very difficult, because the viscosity of that CMC solution will be more higher. So, in that case the entrainment of that kerosene will be more difficult, more resistance will come by that liquid. So, their contact of that kerosene and the carboxymethyl cellulose high viscous liquid will be that less, in that case mass transfer will be very less, even more interfacial area will not be produced whenever you are using high viscous liquid. Also their energy supplied will be requiring more, in that case you have to that consume more energy to get that more entrainment. So, that is why you can say that this it depends on that entrainment characteristic depends on the physical properties of the system as well as the geometry of the system. Now, there are several correlations also available that I have shown in the table. In the downflow systems, we have developed one correlations based on the different operating parameters, and in that case it is very difficult to get that one that mechanistic model to interpret the entrainment characteristics of the gas for the gas liquid operations. For the gas liquid operations, you can actually interpret this, or you can predict that entrainment of the gas, how much gas is entrained there by that making a empirical correlations. So, for that what you have to do, you can do dimensional analysis based on the different operating variables. Now, different operating variables for this downflow system for the entrainment of the gas is like liquid velocity, density of the liquid, viscosity of the liquid, surface tension of the liquid, gas density, if you are using air then air density, viscosity of the air or gas, column diameter, and also that that is called nozzle diameter. Even also you can say that pool of the liquid, that is that height of the pool of the liquid inside the column. So, that should be also considered, because if you have more pool of the liquid there, you will see that more resistance to drag of that droplet or gas into the liquid. So, based on which you have to do the dimensional analysis either by relief method or that Buckingham Pi theorem to get that different dimensionless groups, because you can get different dimensionless groups for that, like QR, that is QG by QL. Here QG is in this slide it is shown that QG is volumetric rate of gas entrained there in the column, and QL is the liquid flow rate, volumetric liquid flow rate, which is that allowed through that rotameter and through the nozzle and creating that liquid jet. And then other groups like DR, in that case that nozzle diameter to the column diameter is one important factor. If you increase the nozzle diameter to column diameter, then you can get less energy supplied there, then entrainment will be less. And also ASR is one important, in that case that height of the liquid and also that diameter of the column, that is HC by dN, you can say that ASR. And RJ, Reynolds number based on the jet velocity, is another group. This is very important because in this case if you are having a more jet velocity, then your Reynolds number will be very high. So, your turbulent conditions will be created, and based on which you can have the breaking up of the bubbles, the bigger bubbles whatever forms in the impinged or plunging region or intense mixing zone there. So, you can get more finer bubbles at high Reynolds number of this jet. And also another important factor is Weber number of the jet. In that case, this Weber number is basically that rho into u square d by sigma. In this case that rho is the density of that liquid, and u is the z velocity here should be considered, and then d j, that means here jet diameter will be considered here. So, Weber number of jet will be considered as that rho u square dj by that sigma. So, in this case if you are having more that narrow liquid jet, you can get more finer bubbles also or more entrainment there. Even if you are allowing that that multi nozzle jet there, so in that case you can get more entrainment of the gas there. So, that is why it is very important. Also surface tension effect also important there. If you are considering the constant jet velocity and that liquid velocity, and also you can that jet diameter is controlled, then if you are increasing more surface tension or if you are adding some surfactant there, you will see the surface tension will be less, then you can have that more finer bubbles there, more stable bubbles will be there, more finer bubbles will be produced, the swarm of bubbles will be produced, the population of the bubbles will be more, then gas entrainment will be more there, because of which that more finer bubbles you can get there. So, this is one important factor, and Froude number is also important there, if is there any gravity effect or not. If suppose this liquid jet is producing from the long distance there, so in that case gravity effect will be more, whereas if it is actually produced in the near about that plunging liquid position, then you can have that less gravity effect there. So, that gravity effect will give you that that by this dimensionless groups Froude number. So, we can have these correlations based on that operating conditions and the entrainment characteristics based on the experimental observations, and we have proposed here one empirical general correlations by which you can say that at which liquid jet velocity will give you the what amount of entrainment of the gas in the downflow system for getting the more contact area between gas and liquid there. So, that depends on that that entrainment amount of gas there. So, based on these correlations you can of course obtain the that amount of gas entrained in the pool of the liquid by this liquid jet system, where ejector will be used for that creation or development of the bubble there in the downflow system. So, we have discussed how that ejector can be used for process intensification, for getting more contact between gas and liquid, more for more finer bubbles formation, more droplet formation, more finer droplet formation for that chemical engineering operation. Like one example I am giving that here, like suppose droplet formation, if you are suppose extracting some propionic acid from the waste liquid. So, in that case, that water which is reached by propionic acid, and if it is actually in contact with the paraffin or some other organic liquid, aromatic ether or some other octanol or decanol, if you make it contact with that propionic acid reached water with that decanol, then you can get that contact area between that immiscible liquid of decanol or you can say paraffin, and then through that interfacial area of that droplet where that propionic acid will be transferred from that liquid to the decanol. So, this process you can apply for the separation of that propionic acid from the liquid to the organic liquid. After that, then you have to distillate it, then so that you can separate those propionic acid. So, this can be utilized here in the downflow systems also by ejector system. In this case, what you have to do that in this case that propionic acid reached water should be supplied through this in this column as a jet, and then it will be plunging into the pool of the liquid, where that that one portion volumetric portion of the paraffin or decanol should be that there, and whenever this liquid will be plunging, there will be formation of droplet of that droplet of that decanol or paraffin there, and whenever this droplet will be forming and it will be coming downward against its buoyancy effect, it will reside for longer time, and then that you can get the more contact time and more contact surface area, and then you can get more mass transfer of this extraction of this propionic acid to the that decanol. After that, you have to separate it by this distillation process. So, this is very interesting application where you can intensify the process, chemical engineering process, by this ejector system in the downflow system. So, I would suggest you to read further about this ejector system, how it can be applied in this book here in the inverse bubbly flow system, how these bubbles are forming and how it will be that inversely flowing, and how it can be applied for different chemical engineering process for their intensification. Even I can suggest more references to go further to get the more information about this ejector system for the chemical engineering operation there. So, I think we have discussed a lot of things about this ejector system for the chemical engineering process intensification. In the next lecture, we will discuss something more about the hydrodynamics and transport phenomena of the ejectors induced downflow bubble column system, based on which that how mass transfer actually effective and how intensify that chemical engineering operation in this system based on hydrodynamics and transport phenomena. So, thank you for this lecture today.